Okay, so let's say that you have some formula that you want to integrate, but you don't know how to integrate it as a whole. However, you know how to integrate or differentiate x alone. You know how to integrate cosine or differentiate cosine of x alone. So, at an initial glance, with the knowledge that you have, you might think that it's very hard to or impossible to integrate this. However, there's something called integration by parts. Now, with integration by parts, there's this formula that you could use that could take this formula or this integral that you can't differentiate and you could change it into a different form that you know how to integrate. Now, personally, this formula looks kind of scary and I had trouble memorizing it when I tried studying this subject. However, this is actually something that you already know. So if I say that I have this equation, so if you have u times v and you wanted to differentiate it. Now, this is one way of saying you want to differentiate u and v. So then, and u and v are different formulas, like u could be x or x squared, and v could be cosine of x or some complicated formula. But we just say we denote it as u and v. Now, if you wanted to differentiate this, now you probably already know it. So it's differentiation by product rule. So it's going to be u times v prime plus v times u prime. Now, you probably know this formula or memorize this formula. Now, if you wanted to know or understand why this formula came to be, the derivation is kind of long, but I'll link it in the description. Like you could pause the video and try reading this, but it needs some prior knowledge of how differentiation works, so I'm not going to cover that in this video. Now, usually differentiation follows some patterns. So for example, if you have x to the power n and you wanted to differentiate that, now there's another way of saying you want to differentiate something. So if you write d over dx, that means you're trying to differentiate this thing inside it. So if you want to differentiate d over dx, then of x to the power n, now as you could see, it follows some pattern. So n times x, n minus 1. Now, as I said, you could use that formula, which I won't get into this video. So it looks like this, which is just the slope formula. Of course, limit to 0. Now, slope delta x, delta y over delta x. Now, you probably already know this formula, and that's how this formula came to be. But as I said, it's in a different form. It's for a different video. Now, if I put this formula inside f of x, or I put this formula inside inside this part and replace it instead of f of x, then you get, like, for example, x to the power 1, and you put it inside this formula, you get some pattern, like this thing. So instead of trying to use this formula every single time you want to use a derivative, you just follow this, you memorize these patterns, and then you use them. Now, this is one of those patterns, okay? And as you could see, it's extremely long trying to trying to differentiate that by hand, and therefore you just use this formula instead. Now, with this formula, you could bring it into another form, which is what we're going to use for integration by parts. So, and to make it clear how this formula came to be, we need to use another notation to represent this. This is called Lebniz notation. So instead of saying this for differentiation, we say d over dx. And v prime, instead of saying that, we say dv over dx. Now, when you say dx, they're talking about something that's incredibly or infinitely small, infinitesimally small. That's what they said. But pretty much this is just another notation for differentiation. So dv over dx, then du over dx. Now, you probably know this from before, but the definition of integration is the Riemann sum. So you have a bunch of rectangles, and that somehow represents the graph. So there's some width, and there's a height. The height is going to be like f of x. Like if we say that this is f of x, then this height will be f of x at that position, this position, and this position. And integration, what integration does is that it gets the limit of this variable to be 0 by using the Riemann sum. Now, when that happens, it becomes dx. So when you see the integral of f of x dx, this is just saying the sum of f of x times dx. Now dx is that infinitesimally small width, okay, that you're multiplying with f of x to get some rectangle. And this is the definition of integration. So if we try using this formula and putting it over here, so we integrate both sides, then look what happens. So we integrate this part, and we integrate this part, and of course times it by dx. Now, as you could see, here there's dx, and here there's dx, and it just cancels out. And actually, if you integrate a differentiated thing, then it would just cancel out. So u times v. Now, over here, we could just split it on the plus. So we could say u times v is equal to the integral of u times dv over dx. And then the dx, of course, we bring it here, plus integral of v times du over dx times dx. Now, look what happens. Dx cancels out. So then we just get this formula, which is the formula that you saw over here. So this is how it was derived. Now, how do we use this formula? Now, it's kind of tricky how to use it, and I'm going to go into detail on how to know which variable should be u and du and in a bit. But for now, let's just say, okay. So now when you're integrating, now usually integration is just simple. Like you have some formula, for example, integral of cosine x. Now this is simple. Like you could just bring it into form like when you differentiate sine of x, it becomes cosine x. So the antiderivative, okay, when you integrate cosine x, it's going to be sine x. So this is kind of simple. Now the goal of most of the integration questions is that you want to bring this part inside to a simpler form that you know how to integrate. Now here, if you just look at it, it's hard to integrate it. But if we somehow bring it into this form, then we could know how to integrate it. So let's try doing that. So now we have x times cosine x. Now, no matter what you do to cosine x, it won't disappear. So if you integrate it, it's just going to be equal to sine of x. If you differentiate it, it's just going to be negative sine x. So it's hard to remove this. Okay, so we want to remove something to make it simpler. However, if we integrate x, we get x squared. And if we differentiate it, we get 1. So as you could see, if we somehow remove x by differentiating it, then we could get a simpler formula that we know how to integrate. So this might seem a little arbitrary, but I'll say that x is going to be equal to u. So u is equal to x. Okay, and that denotes this part. U, okay, we say that this is x. Okay, and as a result, du will be all this part. This is actually dv. I don't know why they chose u and v for this, but yeah. So this all is going to be dv. So u is equal to x, dv is going to be equal to cosine x dx. Now let's try differentiating this. So when you differentiate u, we multiply it by, or we use this form function, d over dx, and from that, when you apply differentiation on x, it turns into 1. From that formula that I just showed you, x to the power n turns into n times x to the power n minus 1. So x to the power 1 is going to be equal, would be when you differentiate it. So it would turn into 1 times x 1 minus 1, which is x to the power 0. So, or just 1, because x to the power, anything to the power 0 is 1. So it's just going to be 1. Now here, we don't know how to simplify this further. D over dx. Now over here, let me just bring this down. So now we have dv is equal to cosine x dx. And if you look over here, we have uv and we have v du. Now, as we said, u is x, dv is going to be cosine x dx. And now we want to get these two over here. So how do we get v? We have dv. If we integrate it somehow, we might be able to get v on its own. And du is, we already have that over here. So du is going to be equal to 1 times dx. So we have u is just this thing, x. So we could say x times, now v, we still don't know, is equal to the integral of u, which is x, times dv, which is cosine x dx, and then plus this other integral. So we want to find this other integral. So v, as I said, we still don't know it. Du is going to be 1 times dx. Okay, now how would we find dv? Or v? We have dv and we want to find v. So we could bring dx to the other side. dv over dx is going to be equal to cosine x. So now if we integrate both sides, as you can see, dx cancels out. And we get cosine x dx, integral of cosine x dx. So now the integral of cosine is going to be sine x. And the integral of dv over dx, okay, as you can see, dx cancels out. So it's just going to be v. Somehow the integral cancels out. Now, as you can see, now we have v. Now we could replace all the empty parts that we have here. So v is going to be sine x. Here it's going to be sine x. Now, this is the original integral that we didn't know how to integrate. However, now we have this part and this part. So we could break this formula down into separate parts. So we could say integral of x times cosine x dx, which we originally didn't know how to integrate. Now, as you can see, there's some byproduct. So x times sine x. Then when you bring this to the other side, you're going to subtract. Minus integral of sine x. Now 1 times sine x, it's just going to be sine x, so I'll remove that. And dx. Now we have this formula that we didn't know how to integrate, and now we have some, we don't need to integrate this further. This is going to be part of the solution. Now we have this other integral. Now this other integral, it's a very trivial integral. Now it's simple how to integrate it. So sine of x, that's just going to be negative cosine x, because when you differentiate cosine x, that turns into negative sine x. So when we do the opposite, then we get this. So now cosine x minus, and there's already a minus here, x times sine x. So if we want to know the answer, this is going to be the answer. So x sine x plus cosine x. Give me a second, I'll just make sure this is true. Yeah, okay. Now, as I said, the order, like what thing that we chose over here to be, uh, oh, I removed the formula, but what we chose is u or v was kind of, or dv was kind of arbitrary. So there's some simplification, okay, on what to choose u and dv. So as I said, the point of integration is to take some formula that you don't know, or take some formula that's hard to integrate, or like at first glance impossible, and you want to convert it into another form which is simple for you to integrate. And from that, okay, so if you want to do that, okay, you need to make it simpler. However, if you look over here, let's say log, or just ln x. So if you have ln x, okay, what's the integral of ln x? You don't know. And if I didn't tell you what the integral of this was, then you would you would think that like it might be even impossible to do this. However, if we okay, so we should always try to differentiate this. Now look what happens to u. U just stays the same over here, and then over here it's differentiated. So we know that differentiation of ln x is just going to be 1 over x. So that's pretty simple. So we want to do that always first. Okay, so that's what they mean by doing log first, like in this order. And now inverse, like even I don't memorize the formulas, but sine negative, like I derive them always. Now sine negative 1, it's going to be some formula like square root 1 minus x squared or something. Now this is hard. Now this is the differentiation of sine negative 1, or in arcsine. Now inverse, it means inverse trigonometric. Now inverse sine, or arcsine, it differentiates to this equation. However, if you try like it's hard to think what would integrate to sine x, arcsine. So you should do this second, because you want to, as I said, you're trying to differentiate the hard part, because that's the thing that's stopping you from solving the integral. So you want to do the inverse first, because you know the differentiation of the inverse function. Now, as I said, we want to simplify the equation. So we choose algebraic. Now, why is that? Now, look over here. We have x, cosine x. However, when we differentiated x, we just got sine x on its own. So we want to, uh, if we have like algebraic and trigonometric multiplied together, so we want to differentiate the algebraic. So we just have it on its own. And by the way, sometimes you need to use integration by parts multiple times to get the answer. Now trigonometric. Now it's simple to do trigonometric integrals, so you usually want to keep it for last. Yeah, like sine x. If you integrate that, just gonna be negative cosine x. So it's not too hard to integrate trigonometric. So you want to leave it until you remove the hard things to integrate first. Now exponential, if as you could see, integral of e of x is just going to be e of x. If you differentiate e of x, then it's going to be just e of x as well. So exponential functions are extremely simple. So you should consider that last for u, because you're choosing that to differentiate. So you want to choose the thing that's easiest to differentiate and hardest to integrate. And that's integration by parts. Now, of course, you would want to solve more to get used to it, but that is all.